Hello and welcome to this last video of my playlist about the preparation of aryl fluorides. As usual, there's a copy of the slides under the Posts tab of my channel. In this video we'll have a look at aromatization and ring-forming reactions for the preparation of fluorinated arenes and heteroarenes, mostly heteroarenes. A few fluorinated reagents are prepared on a large scale by electrofluorination of CH bonds in hydrogen fluoride, or from alkyl chlorides and hydrogen fluoride. Some of these building blocks are readily available and inexpensive. These include tri- and difluoroacetic acid and their simple derivatives, like esters or amides. Trifluoroethanol and trifluoroacetone are also available, as is ethyl trifluoroacetoacetate. The latter is made from trifluoroacetyl chloride and ketene and is a valuable intermediate for preparing trifluoromethylated heteroarenes. Trifluoroethanol can be converted into a torsylate or mesylate, but these sulfonates do not react well with nucleophiles. In fact, trifluoroethyl electrophiles are extremely unreactive. Their rate of reaction with potassium iodide in acetone is about 4 orders of magnitude smaller than that of propyl torsylate or bromide. In this example, trifluoroethyl triflate was treated with an aryl Grignard reagent, but no trifluoroethylation occurred. The electrophile was only attacked at sulfur, not at the methylene group. Similarly, trifluoroethyl iodide gave only 37% of an ether when treated with sodium phenoxide in DMF. Nucleophilic attack occurred mostly at the trifluoromethyl group. A comparison of the structure of trifluoroethyl sulfonates with ethyl sulfonates shows that trifluoromethyl groups shorten and strengthen adjacent CO bonds and thus lower their reactivity in SN2 reactions. Trichloromethyl groups behave similarly. This can be rationalized by a delocalization of an oxygen lone pair into the antibonding CC sigma orbital. Cyanomethyl electrophiles, on the other hand, are much more reactive toward nucleophiles than unsubstituted alkyl electrophiles, probably because of assistance by the empty antibonding pi orbitals of the cyano group. Anyway, it is possible to eliminate hydrogen fluoride from trifluoroethyl tosylate, as shown here. The resulting difluorovinyl ether is a valuable reagent for preparing fluorinated heteroarenes, as I'll show you in a minute. Another way to prepare difluorovinyl ethers is by reduction of trifluoromethyl ketones. This can be achieved with a mixture of metallic magnesium and chlorotrimethylsilane in THF or DMF. I'll show you now some specific examples grouped according to the type of heteroarene formed. Here a pyrrolidinone was first converted into a geminal difluoride by treatment with dust. Beta elimination and dehydrogenation with manganese dioxide then gave a fluorinated pyrrole in low yield. In this related example, a higher yield was attained. Both water and hydrogen fluoride were eliminated by treatment with cesium carbonate in acetonitrile, which also caused decarboxylation of one of the ethoxycarbonyl groups. Here, such an elimination was achieved with sodium hydroxide in aqueous methanol. The geminal difluoride was prepared by electrophilic fluorination of a pyrroline with a select fluor, but the yield of this fluorination was low. With potassium carbonate instead of sodium hydroxide, no hydrogen fluoride but only hydrogen bromide was eliminated. Fluorinated pyrroles can also be obtained from aminoethyl alkynes. In this example, such an alkyne was prepared by addition of a propargylic organolithium compound to an imine. Cyclization and dehydrofluorination proceeded at room temperature with 10% of gold chloride. Bases such as DBU, however, did not bring about cyclization but only the elimination of hydrogen fluoride. Similarly, fluorinated furanes can be prepared by oxidative cyclization of hydroxyethyl alkynes. Here iodine chloride was the electrophile and the dehydrofluorination went to completion when the crude product was treated with silica gel. This here is an uncommon strategy to prepare 2-fluorofuranes, also because difluoroallenes are not readily available. The cycloaddition to benzaldehyde was catalyzed by 2% of a gold carbene complex and 2% of silver hexafluoroantimonate. A strong base was also required. Difluoroallyl thioethers can sometimes be cyclized with strong bases, as in this example. The initially formed 3-fluorothiophene was lithiated once more and then silylated. The starting material of this example can be prepared from 1,4-butylenediol by electrophilic fluorination. Despite the low reactivity of this ditosylate, it could be cyclized to a tetrahydrothiophene by treatment with sodium sulfide. Fluorination with select fluor and base-induced dehydrofluorination then yielded tetrafluorothiophene. Enones are convenient starting materials for pyrimidines and pyrazoles, and from fluorinated enones, fluorinated pyrazoles can be obtained, as in this example. With aqueous ethanol as solvent, mostly one regioisomer resulted, but with other solvents, product mixtures are usually formed. The required enone was prepared from trifluoroethyltosylate by conversion into a vinylborane followed by acylation at carbon. Heating aldehyde hydrazones with tribromofluoromethane and a ruthenium catalyst can also yield fluorinated pyrazoles. From the various intermediates, bromide was eliminated more readily than fluoride. The driving forces of this reaction were formation of two new carbon-carbon bonds and aromatization. This here is a photochemical version of the previous example, with dibromodifluoromethane instead of tribromofluoromethane. In this example, a fluorinated imidazole was prepared from an imine and a large excess of an isothiocyanate. The latter acted both as a carbon nucleophile and as a source of difluoromethylene. The carbanion formed by fluoride-induced desilylation added first to the imine to yield a cyclic thiourea. Difluoromethylene then alkylated this intermediate at sulfur. Here an amidine was alkylated at nitrogen by a copper carbene complex. With the aid of sodium hydride, the intermediate was then cyclized to a fluorinated imidazole. Like imidazoles and pyrazoles, also 1,2,4-triazoles, the product of this reaction, are highly aromatic and stable. Here the triazole was formed from an imidoyl chloride and phenylhydrazine. Unfortunately, the synthesis of the imidoyl chloride was lengthy and expensive, and a more convenient approach would probably have been electrophilic fluorination of a lithiated triazole. 1,2,3-triazoles are less stable than 1,2,4-triazoles and are almost never used as a structural element of drugs or agrochemicals. In this example, such a 1,2,3-triazole was prepared from an alkyl acid and methylated difluoroethylene. This is an example of electrophilic fluorination of an alkynyl oxime. Gold and silver catalysis yielded a fluorinated oxazole in excellent yield. Earlier I showed you a procedure for reducing trifluoromethyl ketones to difluorovinyl ethers. These are nucleophilic at carbon and can undergo Michael addition to enones. The resulting 1,5-diketones can then be cyclized to 3-fluoropyridines by cyclocondensation with ammonia. In this example, a fluorinated pyridine was prepared by treatment of an alkynyl imine with a benzylamine. The imine was obtained from a trifluoroacetamide by deoxychlorination and coupling with a terminal alkyne. The pyridine ring was formed by a sequence of dehydrofluorinations and an electrocyclization, as sketched here. Such reactions almost never work when planned and are usually discovered by accident. Here a pyridine was formed by heterodiels-Alder reaction of an alkyne with the oxime of an enone. Cesium pivalate and a rhodium complex catalyzed both the cycloaddition and the dehydration. This is an interesting example of the preparation of a fluorinated pyridone. Michael addition of a sulfonyl fluoroacetamide to a trifluoropropene gave an intermediate from which phenylsulfinate was eliminated more readily than fluoride. Cyclization by addition-elimination then yielded the final product. Another useful fluorinated building block is fluoromelonic acid. Fluoromelonates can for instance be transformed into pyrimidines by cyclocondensation with amidines. Even under alkaline conditions, no nucleophilic displacement of fluoride occurred. Fluoride is a poor leaving group in aliphatic SN2 reactions, especially in aprotic solvents. Only during aromatic nucleophilic substitutions or from vinylic positions can fluoride be displaced by an addition-elimination mechanism, but not when bound to sp3 carbon. Malonates are highly enolized though, and a nucleophilic displacement of fluoride could not be completely ruled out in this instance. Cyclocondensation of fluoromalonic acid with anilines and an excess of phosphoryl chloride yielded halogenated quinolines. Hydrogenation then led to a selective cleavage of the carbon-chlorine bonds. Fluorinated quinolines can also be obtained from trifluoromethylanilines. Here, such an aniline reacted with an excess of lithiated butyronitrile to yield a substituted 4-fluoroquinoline. 2 or 4 trifluoromethylanilines eliminate hydrogen fluoride when treated with strong acids or bases, and the initially formed difluoroalkenes are good Michael acceptors. Here, this intermediate reacted with the lithiated nitrile and cyclized and aromatized. This is another example of the use of ethyl trifluorodiazopropionate as a starting material for a fluorinated heteroarene. Heating with a benzoic acid imide and catalytic rhodium gave a fair yield of an isoquinoline. Interesting is the unexpected intramolecular electrophilic attack of the difluoroacrylate at the deactivated benzene. This again shows that difluoroethylenes are more reactive and more electrophilic than non-fluorinated ethylenes. Despite this high reactivity, difluoroethylenes can sometimes be isolated, as in this example. A substituted styrene with 2 terminal fluorine atoms was prepared in a one-pot procedure from trifluoroethyl tosylate. Addition of butylithium to the cyano group led to cyclization and formation of an isoquinoline. A similar strategy can be used to prepare fluorinated indoles. The excess of sodium terzbutoxide in the last cyclization step did not cause displacement of the second fluoride. Treatment of lithiated anylides with bromodifluoropropene and a palladium catalyst led to a clean displacement of bromide without allylic inversion. The product did not cyclize right away, but required treatment with palladium and bases at 80 degrees Celsius to achieve cyclization by intramolecular Heck reaction. Treatment with a secondary amine then yielded an aminomethyl indole. This here is a rare example of the preparation of an aryl fluoride by aromatization. Careful treatment of the initial Diels-Alder product with a silica gel led to elimination of only one fluoride, and dehydrogenation with DDQ then yielded a fluorobenzene. Under more vigorous conditions, however, the Diels-Alder adduct might have eliminated both fluorine atoms and aromatized at once. The difluorobutadiene was prepared from cinnamic aldehyde and a trifluoromethyl anion equivalent, followed by a reductive defluorination. Perfluorinated thiophene oxides are reactive 1,3-dienes and can undergo Diels-Alder cycloaddition to alkynes, as in this example. The thiophene oxide was unstable and dimerized already at 0 degrees Celsius. Therefore, it was generated in the presence of the dienophile by reduction with metallic zinc. Here are some more examples which you can also find in the description of this video. This was the last video of this playlist. Hope you found it useful and stay tuned for more videos on organic synthesis.